This is my title, X-ray Study of Kyoto Millennium Supernova Remnant. I am Katsuji Koyama at Kyoto University. These are the main points I want to make today. First is the origin of the galactic cosmic rays and the acceleration mechanisms. Secondly, the nuclear synthesis in the supernova and the supernova remnants. And number 3, the study of non-equilibrium plasma. This research was done by Kyoto University group, and we had a glimpse of the X-ray universe through these studies. Then in the first place, what is X-ray astronomy? But why do we need to study X-ray astronomy? Now, all the astronomical objects emit X-ray as we know, but the cosmos looks completely differently when it is looked at through the visible light and through X-ray. In this visible light, this is the cluster of the galaxies. And this is the biggest constituent of the cosmos. The cluster of galaxies is literally the aggregate of galaxies. It consists of 100 galaxies, and each galaxy has 100 billion stars. And with visible light, this is the plasma, and this is the sun. The temperature is similar to the temperature of the sun. So this is what we look at through the visible light. And if we look at the exactly same area in X-ray, this is what we get. This is the X-ray cosmos. It looks so differently from the visible light. It looks like one huge the ball of fire. The X-ray looks at the 50 million degrees plasma. So the cluster of galaxies looks like this, a chunk of plasma. It is high in the temperature. And on top of that, the mass of this entire plasma is this big, 10 to the 14th solar mass. And the star's weight through visible light is 10 to the 11th times 10 squared, so it is 10 to the 13th solar mass. So the cosmos through X-ray weighs 10 times as big as the cosmos through visible light. So these two cosmos look completely differently. And not only that, the mass we can see also is different, 10 times more with X-ray. This is a surprising fact. And the X-ray astronomy now covers the entire cosmos, but I don't have much time to explain everything. It will take up a whole day. So today I will focus on a star observed with X-ray. This is another example. This is the Orion Nebula through the visible light. You see the black spots. This is the dark area. And then, as you can see with the radio wave, this is the chunk of the molecular cloud. And this cloud shut the light of the star. So you will see this as a pitch dark area. And is it really dark? Is there not anything here? And if we look at this area through X-ray telescope, this is what we get. This dark area, part of this area, is magnified here on this panel. You see lots of bright dots. These are stars emitting X-ray. What it is that the stars are generated from these molecular clouds. So these are the baby stars. The age is here written. 100,000 years. You may say this is pretty old, but if this is a human, this is just a day one after the birth. So the baby star are already as bright as this with a strong X-ray. Next. This is the other cloud. This is a video. This is the 1 light year square. And we observed this with X-ray. You see the bright dots here, and all of them are protostars. This is a very narrow space in the cosmos, but it is filled with or crowded with lots of protostars. That means that the protostars are born in a group. This is the age of these protostars. So this is also the day one of after the birth. If this is a human, they are really a babies, and then they blink, and it is almost like a baby crying just after the birth. This is a snapshot of 5,000 seconds. And so this covers 1.2 days. And if it is the human life, it is 1 second. In that short period of time, there were the strong blinking, and the brightness is 100,000 times brighter than the light of the sun, emitting the X-ray. This is really a big birth cry of protostars. This is how the stars are created. A baby, the human baby, is not that noisy, but the protostars, their cry is the 100,000 times louder than the star, matured star. Once the stars are matured, which is called main sequence stars, the X-ray becomes quieter, and the 100,000th, but it is visible in visible light. That's why we can see these stars. And then toward the end of the life of the star, if it is the high mass star, at the end of the life, X-rays are again very bright. And this is called supernova or supernova remnant. Now, speaking of supernova and supernova remnant, what are they really? If the star is very heavy, it becomes bright with nuclear fusion, and the heavy elements are generated. In astronomy, heavy elements is the one heavier than helium, so it is not very heavy. It is relatively heavy. The heavy elements, the carbon and heavier elements are called heavy. And then these heavy elements will be accumulated like an onion in layers due to the nuclear fusion. The helium turns to carbon, and carbon turns and oxygen and becomes neon and silicon. In this sequence, gradually the heavier elements will be accumulated at the center. Finally, the ion. But depending on the mass of the stars, the core becomes different. The 8 to 10 times of solar mass, if the star has this weight, and then the nuclear fusion goes as far as neon and then stops. When it stops, the pressure will be lost, and this chunk will start to shrink. Without any pressure, it will shrink to the ultimum, but there are the degeneracy pressure. This is the quantum mechanics force. The quantum mechanics is something about a very small things, but in this huge cosmos scale, the quantum mechanics is useful. And then this types of star is called white dwarf. The white dwarf itself is very stable. If it is not affected by some other force, it can stay hundreds or billions of years. But sometimes gas will be irradiated to the white dwarf, and then it reaches the Chandrasekhar limit of the pressure. And then the white dwarf will collapse and start the nuclear fusion. The C, O, and N will go through the nuclear fusion to be an ion. And then this releases a huge amount of energy. And this energy will blast the entire star. It's like a huge version of the hydraulic atoms. And then this is what we call the type 1a supernova. And as you can imagine, the huge amount of ion will be scattered into the cosmos after this. And this is called type 1a. Please keep this name in mind for now. If the star is heavier, more 10 times heavier than the solar mass, and then their life course is a little bit different. The nuclear fusion goes as far as iron, and the core becomes iron. And the iron cannot go farther than this process. And the binding energy is the smallest or largest for the iron, the most stable. So the process stops here. And then the core becomes bigger, grow. And then it becomes heavier, and due to its own weight, it cannot sustain itself. If the human gain too much weight, we cannot sustain ourselves. That's the same. If the core becomes too big, it cannot sustain, and it starts to shrink very rapidly. This is called the collapse. And once collapse happens, this gravity energy is released to the outer area, and the elements in the outer areas are expelled to the outer space. He and Co and neon are expelled to the outer space. This type of blast is called core collapse supernova, or CCSN. The gas in the surrounding will be scattered, and in this supernova, the relatively light, heavy elements are expelled. In the previous one, the iron was scattered, but in this case, the more lightweight the elements are scattered, and this is the origin of the current constituent of the cosmos. What happens to the core? Unlike the white dwarf, it cannot be supported by the degeneracy pressure of the atom. So eventually the core becomes a neutron star or a black hole. You might have heard the word black hole, and the neutron star is the precursor of the black hole. And both of them are a very extraordinary star. The neutron star is heavier than the sun, but the diameter is only 10 kilometers across. And then what about the density? This size chunk, neutron star, how much does it weigh? 1 billion tons. You may not believe it, but this is true. This kind of unimaginable body exists in the cosmos. These two types of supernova have the blast, and there is a blast wave, and the shock waves are created, and this shock wave creates the hot plasma of several tens of millions of degrees Celsius, and this is called supernova remnant. These supernova remnants is very high in the temperature, so naturally emit a strong X-ray. This is why at the end of the life, star becomes very bright. So I have talked about the supernova and the supernova remnants, so let's move on to the origin of the galactic cosmic rays and the acceleration mechanisms. This is the cosmic ray. This is not the spaceship. The Japanese word sounds very similar. And the cosmic ray is the treasure trove for the Japanese researchers. There are lots of Nobel Prize in physics for Japanese researchers. For example, Hideki Yukawa came up with an idea of the meson theory, and this was confirmed in the cosmic ray. And Dr. Koshiba first detected neutrino in the sun and from the supernova. Neutrino is also one of the cosmic rays. And Dr. Kajita found out that the three neutrinos they exchanges each other. This is called the neutrino oscillations. And because of this, he proved that the neutrino has its mass. And all of the three got the Nobel Prize in physics. And 2 months from now, in this place, I will invite Dr. Kajita to give us a lecture. So please come back in 2 months. The title of his keynote lecture will be The Secret of the Universe Explored from the Outer Space. And I already asked him to use the layperson's words to explain about his research. So I would like to invite all of you. There are other lecturers who will be invited, but I wouldn't introduce them in details today. And then next is about the cosmic ray. What is the cosmic ray? It was discovered 100 years ago by Hess, a German. And we know what it is. That is the highest energy particles in the universe. This is a graph of a cosmic ray. The horizontal axis is the cosmic ray energy. The electron volt is the unit. You may not know this, but it is EV. Just remember these initials. And the vertical axis is the number of the cosmic ray at a particular energy level. This is a spectral. And is it really the highest energy particles in the universe, you may ask? The highest energy humankind can make exists in the borderline between Switzerland and France. The 30 kilometers underground. This is a very big accelerator. And this is called LHC, Large Hadron Collider. And it is written in the red line, the 10 to the 13th or 10 to the 14th. And the cosmic ray is much stronger than the energy that we can create. Yes, the cosmic ray is the highest energy particles in the universe. You see this bending area. This is called the knee. The energy below the knee is the galactic origin. And the energy higher than knee is the extragalactic energy. So we know what the cosmic ray is, but where is it generated and what kind of acceleration mechanisms is at work? We didn't know. And Dr. Hayakawa, my mentor, proposed the supernova theory, but there was no empirical or experimental verification that followed. But we discovered that, and we found out that the energy, the cosmic ray, where it comes from, we used the supernova SN1006 to elucidate that. This is the X-ray image of SN1006. You see crescents, and this shows the intensity. And again, when we take the spectrum, we see the red curves. The horizontal axis is energy in kilo electron volt. And how do we get this, and what is the X-ray with this spectrum? This is the synchrotron radiation. The synchrotron radiation is the X-ray at the rapid speed. And from this shape, we can tell the energy level as shown in this formula. The magnetic field and energy levels are necessary to know this. In SN, the magnetic field is 1 microgauss. And then the electron energy here is 10 to the 14th electron volt or higher. So the energy level is close to the knee level. Here, the acceleration is taking place to that energy level. Now we know the origin of this cosmic ray. Then why this high level of energy, or the particles with that high energy, is generated? So what is the mechanism of accelerator? We didn't know that in this case. And again, we looked at the same SN1006 to know that. This is the magnified image of this area. This area, the cross-section of the X-ray is this. And you see the zigzag, and there is a sharp peak here. This is a shock front. And the shock front here to this front, it moves forward to this point. 2003 and 2012 observations are compared 9 years apart, and there is an outward motion of the shock front. This seems to be quite small, but in the actual speed, it is 6,000 kilometers per second. The bullet train is much slower. It is 300 kilometers per hour, so it is the many magnitude difference. So this shock front is spreading outward at this extremely rapid speed, and the upstream is outside, and the downstream is inward. So the shock front is moving to the upstream at a very rapid speed. This is the cross-section, very unique. The upstream is very quick, and the downstream has a slower tail. Why do we have this kind of structure? This structure really is the acceleration mechanism of the cosmic ray.
And in order to explain this, this is a schematic diagram. Here is the shock front. It is moving 6,000 kilometers per second, and this upstream. This is the quite well organized magnetic field, and this after this the behind this upstream in the downstream the magnetic field is quite disturbed, and electrons are moving between the upstream and downstreams, and against this moving wall, these electrons hit the wall, and this is what I call a ping pong ball in the moving walls, meaning that electrons are accelerated in downstream because it hit the moving wall, and then energy becomes higher. But some of those electrons are lost in the downstream. They are lost from the acceleration zone. So higher energy, the particle becomes, the number of such particles getting smaller. So this is the spectrums. So lower energy particles are found in larger numbers, but once those particles gain higher energy, their numbers become smaller. So compared to the previous graph of X-ray, so this shows the mechanism of acceleration. This is what is called the diffusive shock acceleration. So this is a type of the Fermi acceleration. The Fermi theory was a little bit different in the concept, but this is a type of the Fermi acceleration. And so acceleration, now we understand the mechanism of acceleration, but it takes time for the acceleration because those electrons go back and forth and hitting the moving walls before being accelerated. So how long does it take usually? It can be calculated based on the intensity of the magnetic field and others. And based on this calculation, that this acceleration began 1,000 years ago. So it took like 1,000 years to be accelerated. And this was demonstrated. This has been proven in a document that can be found in Japan, especially in Kyoto. So Fujiwara Teika is a poet in Heian period. Maybe Fujiwara Teika is not well known among non-Japanese, but if you're Japanese, you should know him. And Fujiwara Teika wrote a diary called Meigetsuki. And this is a copy of the Meigetsuki. I received this copy from the Reisenke, which keep this document. And there's the one description in 1006. It says there's very bright supernova, and in the areas of Lupus, it says. So this is a document written about 1,000 years ago. This is a diary by Fujiwara Teika. And I found this document, and I thought I was lucky that I was transferred to Kyoto University, because this research began right after I was transferred to Kyoto University, and I just came across with this old document of 1,000 years ago, and I saw the linkage between the contemporary astronomy with this very old document. And in this Meigetsuki, there are two other records of the supernova. But this is a very famous discovery. And if you look at the history of the supernova or supernova which are confirmed in history, there are only 6 cases. And all the 3 cases which are already documented in Japan and China. So Japan, China had such an old record of those supernovas. And these 3 are also mentioned in the Meigetsuki diary of 1,000 years ago. So this is quite a significant contribution by Fujiwara Teika, a poet. And Fujiwara Teika said those records were not taken by himself, but these are the records taken by the offspring of Abe no Seimei, who is the legendary Indian diviner, and the offspring recorded those records, and then simply Fujiwara Teika pasted. So as you can see, there are different handwritings. So this from the right, so this is the written by Fujiwara Teika, and this blue areas is written by Abe Taishun, and in the middle, in the green areas, this is from the another person. So basically, Fujiwara Teika, the copy and paste the record that is written by the Abeno Taishin. And I thought the Abeno taker is very honest compared to the current student we found in our university. They do a copy and paste a lot, but they don't tell they copy and paste. But Fujiwara taker is very honest. He said he just copy and paste. I spoke this, and then on the other day I said this, but Reise, person from the Reise family, say that he is not. Actually, I said that Fujiwara taker the inventor of copy and paste, but the person who still keep this document say that no, he simply pasted. He didn't copy, so he's inventor of paste. And this is the Greenwich Observatory. Greenwich Observatory is now in museum, and there's such a record just before 1605 of the Galileo's invention of telescope. There's a record of the Chinese and Japanese astronomers. And this is a closer look. So as you can see, Chinese and Japanese astronomers note a new star flaring up in Taurus. The remains are now identified as the Crab Nebula. So this is the astronomical chronology that can be found in the Greenwich Observatory. And this observatory is now a museum. And Kyoto University has a very old observatory. So my wish is to convert this observatory into a museum, but we don't have enough budget. So I would like to ask for your contribution to our project. And in this museum, in this planned museum at Kasan, the observatory, we plan to exhibit the Meigetsky copy of Meigetsky. And this is a reconstruction of eastward night sky of Kyoto in 1054. So on July 5th, 1054. And this is a crescent. Close to the crescent, there's a bright star. And this is a reconstruction of the night sky of 1,000 years ago. And this brightness is as bright as the Jupiter. So such a bright star must be noted all around the world, but there's no record in the Western countries. Only China and Japan has such a record, historical record of this supernova. And this is an X-ray image of this area. Unfortunately, this was taken by NASA, not ourselves, but this is quite a unique structure, as you can tell. And I have a lot of stories about this picture, but I don't have time. But in the middle, you see a dot. This is a neutron star. So this is very heavy. So just hand grabs of the neutron stars weigh like 1 billion kilogram. And 1 billion gram, excuse me. So this is the image taken by NASA. And Dr. Bell, who is going to speak after, discovered the radio pulsar. So radio pulsar is basically a neutron star. And also Dr. Alt, who won the Kyoto Prize, went to the Racing family, which still keeps this old document of the diary of Meigetsky, and he actually looked at the original copy of Meigetsky. So this is just a side story though. And this record is only found in Japan, China, and the Western countries. There are no record. Maybe the Western researchers are not happy with this fact. That's why American researcher came up with this picture. So this is a record of the supernova of 1,000 years ago. So this is a wall painting in the Pueblo Bonito. And this picture was drawn not by the American, but the Native Americans rather than the current Americans. So American researchers do not have anything that they can proud of. Anyway, So now let me explain how the heavy elements are generated in the universe. As I said, heavy elements are the elements which are heavier than helium. And as you know, the universe was born out of Big Bang. So this is the universe out of Big Bang. And it's very flat structure. It's like smooth rippling Pacific Ocean that's evolved into the present universe. This is a cluster of galaxies, and in one galaxy, there are like 10 million stars, and the heavy elements are generated in these stars, and those are scattered by the supernova. And so the supernova, because of the heavy element generated by supernovas, we are here, the human beings are here. Then are there any evidence of this, whether those are heavy elements are scattered by the supernova? So this is a spectrum inside of this. And so this is the spectrum compared to the flat structure I showed before. There are many peaks, as you can see. So those are the X-rays that are emitted by specific elements, and this spectrum itself, we are able to tell that those heavy elements were created by the supernova. And we are able to calculate the amount or quantity of those heavy elements. With that calculation, you come up to the type of the supernova as well. So this SN 1006 was the type 1A supernova, and this has the lightest, and so it's even lighter than the crescent. And those chemical composition depend on the plasma condition. So you may believe that we know the plasma condition already, but this is non-equilibrium plasma. So when it comes to the stable plasma, you might believe that you can already understand, but laboratory plasma is unstable. It changes in a short period of time. So this is a bottleneck of the commercialization of nuclear fusion. And SNR, hot plasma, is also unstable, but then time scale is long. That's why it's crazy stable. That's why you are able to research the plasma. So SNR is better laboratory to study unstable or non-equilibrium plasma. And by this research, we identify the composition of elements. And now we are in the second revolution of X-ray astronomy. First revolution was the inception of X-ray astronomy itself. So this dramatically changed our view of the universe. That was quite big revolution. But that was rather qualitative revolution. But the second revolution I'm talking about is a quantitative revolution. This is just one example. This one's X-ray spectrum. So this is before and after the revolution. Red one is before revolution. A black one is after revolution. And if you look, if you take a closer look, it looks like this. This spectrum comes from the elementary process. Therefore, theoretically, you believe you understand. This has been already demonstrated in a laboratory, but this is wrong. The astronomers, also the physicists, believe they understand. But actually, if you look at these differences between spectrums, so those theoretical prediction was very different from the observational result using X-rays. So now we enter into the second revolution of X-ray astronomy, and this will continue for next 10 years, I believe. So maybe in 10 years, our understanding, our views of the universe will be dramatically changed. So if I am around in 10 years, I can make a presentation once again in 10 years. Thank you very much.